Hi, welcome back. I'm Greg Smith, aka Dr. Frankentosh, and today we'll be looking at part 2 in my series on object-oriented programming in C, polymorphism. If you recall from part 1, polymorphism is the ability of an object to act like or take on the abilities of some other object. So we'll get started right after this on Dr. Frankentosh. Now, if you remember from part 1, we created a class called LED, and it had the ability to flash on and off at a particular rate. The elements of the LED were the pin assignment, the state, whether it was on or off, the delay, how long to be flashing, and then the last time that we blinked, there was an initialization method which would turn on the GPIO pin, and then the blink method, which would determine whether the LED should be turned on or turned off at a particular rate. And then back in the .C code, the new method, we've modified slightly. Now what we're doing is, if you pass in a pointer to a previously allocated LED, it will simply update it with new initialization values. But if it's null, it will call the calloc function and actually allocate the memory for you. So otherwise, everything's the same as before. So let's take a look at extending this capability from a simple LED that blinks on and off at a particular rate to an LED that blinks really fast at a particular rate. And it turns out that if an LED is blinking really fast, it looks not that different than an LED that is constantly on. If you change the amount of time that the LED is on, and you make that small compared to the amount of time that the LED is off, the LED appears to be dim. But if the LED is on equally as long as it's off, it looks like it's only 50% lit. And if it's on most of the time and off just a little bit of the time, it looks bright. This is pulse width modulation. I'm not going to go into a detailed description of it here, but I will give a quick overview. So let's go to the magic whiteboard. So here we are at the magic whiteboard. If you remember from last time, we had an LED that would blink. And the way that it blinked was it would be on for a certain period of time and then off for the same period of time. And that creates a square wave. Now, the distance or the time between peaks is called one cycle. And this time in here is the amount of time that it's on. And this time in here, the amount of time that it's off. And if this one cycle is, say, 10 milliseconds, and the on time is 5 milliseconds, and the off time is 5 milliseconds, we call that a 50% duty cycle. So 5 milliseconds over 10 milliseconds equals 0.5, which is 50%. Now, if we have a cycle time that's short while it's on and then long while it's off, let's say this is 1 millisecond and this is 9 milliseconds, we have 1 millisecond over 10 milliseconds, which is 0.1, which is a 10% duty cycle. Now, when the LED is in this state where it's on for a short period of time and then off for a longer period of time, the LED appears to be dim. And as this cycle time increases, or as this duty cycle increases, and we get closer to cycle times which are long on and then short off, the LED appears to be on. And then ultimately what happens, if you get 100% duty cycle, it appears to be solidly on. Now this is what's called pulse width modulation. The Raspberry Pi Pico actually has PWM built into it, and there's a library that will control the LED and give you really good PWM capabilities. We're not going to use that library today because we want to emphasize the abilities of our code to act like it has polymorphism. So we're going to emulate PWM in our own code. So to get started, we're going to copy the LED.C class into the PWM.C class. This is our interface. So for those of you who are object-oriented purists, you'll notice that the first line here, line 11, actually includes an LED at the beginning of our PWM class. There are some members and methods that we need to add to PWM to make it work. We're going to need the number of cycles that we want to run. We're going to need the duty cycle. We're going to need to know how long to leave the LED on and how long to leave it off. And we are going to add a method to set the duty cycle of the LED. Now back in the implementation, we have the new method. As before with the LED, you can pass in an existing PWM. If this value is passed in, it will not be null, and it will reinitialize the PWM. However, if you pass in null, it will allocate the memory for the PWM. Notice here that I've got an LED pointer. I've cast the LED struct to the LED pointer, and I am calling the LED new function, but I'm passing in our pointer to the LED structure that's in our PWM. And so it's going to initialize the LED for us. Now the next step is to replace or override the existing LED blink method with our own blink method. Again, in object-oriented parlance, this is what's called overriding. Now look at this syntax here. We take the this pointer, we then dereference it to get the LED object. We use the dot notation because this is an actual struct in our this object, in our PWM object, and then we reset the blink method to point to our own blink method. Then to continue on with the initialization, we set the number of cycles that we're going to run, that is the number of milliseconds that we want our single cycle to last, to 10 milliseconds. Then we set our duty cycle equal to the duty cycle method. So this is the set duty cycle method. We'll cover this shortly. Then we call our duty cycle method with the duty cycle that we want it to have. So this can be 10, 20, up to 100%. And in our case, we'll be using increments of 10. So if we pass in 1, that will be 10%. And if we pass in 10, that'll be 100%. So here's the set duty cycle method. As with our other methods, we get the global this pointer. We set the delay on to be the number of cycles and the number of milliseconds we're going to wait. In our case, it's going to be 10 times the duty cycle, and this will be a value from 0 to 10 divided by 10 because we want 10 to be the maximum. Then we'll set the number of milliseconds that we want the LED to be off, and that's the total number of milliseconds in the cycle, and then we subtract off the number of milliseconds that the LED is on, and that gives us the off time. And then finally we store the duty cycle in our PWM object. Next we want to set the delay, and note again, we are getting the LED dereferenced. We are then using dot notation because this is the actual LED structure. So notice that we're using the ternary operator. We are checking the LED state, and if it's on, then we set the delay to whatever our delay on milliseconds is, and if it's not on, we set it to the delay off. So this will set the delay for our blink method. So let's take a look at the blink method. This works very much the way our original LED method worked. We get the global this pointer, and if we have expired our delay time, we reset the last time, we invert the state, and then we get the delay. We set the delay on the LED based on the current state of the LED, and then we update the GPIO pin with the current state of this LED. So this should create a flashing LED that is on for a short period of time when the duty cycle is low, and on for a long period of time when the duty cycle is high. So here back in the main, we have a pointer to the PWM. This is a new PWM, and notice I'm using red PWM in this case so that I can tell the difference between when I'm acting like a PWM LED, but I've also cast the red LED pointer to point directly to the structure. Now this is really, so again, some syntactic sugar. These two pointers point to exactly the same thing, but when I use the one called red PWM, it allows me to get at the elements that are part of the PWM, and when I use red LED, it allows me to get to the elements that are part of the LED structure that are inside the PWM. Also, we have a green LED that's flashing at 500 milliseconds. As before, we have a big while loop that runs forever. We blink the red LED, then we blink the green LED. I've also added a new function which checks to see if the boot select button on the Pico board has been clicked. And if it has been down, then we go ahead and set the state to true. And then when the button is up again, then we reset it to false. And now we're going to update the duty cycle. So up here, the duty cycle starts out at 0, and the duty cycle direction is 1. In other words, we're going to increase the duty cycle every time we press the boot select button. So down here, as long as the duty cycle has not gone up to 5 or down to 0, we're going to invert the duty cycle. So if it gets up to 5, it'll go down. It'll go to -5. Currently, it's at 1, and so what's going to happen is we're going to set the duty cycle to 1. And when it's set to 1, that means it's a 10% duty cycle. The next time through, if we click the button again, it'll go to a 20% duty cycle, and so on until it gets to 50%. And at the 50% duty cycle, it'll start ratcheting down again. It'll go in the opposite direction. So this is just a way of cycling through 0 to 50% duty cycle. So let's go ahead and take a look at that code in action. Let's go to the video. So here I click it the first time, and the LED is dim, and it gets brighter with each successive click. And as you can see, the green LED is flashing along with it, so we have our multitasking capability. And now it's back down to 0. So even though this is an PWM object, we still call the blink method, and because it's slightly different, because we have changed the pointer to the blink method so that it calls the PWM blink method, it looks exactly the same as when we call the flashing LED the green blink method. There's no difference in syntax here, but yet we get two different behaviors because we've implemented our first step towards polymorphism. So, as good as this is, there's still some problems. We really don't want to have to deal with multiple pointers. We don't want to have to deal with this composition. We really want a more smooth interface so that the red PWM LED and the red LED pointers act the same way. We don't have to switch between them. So let's do that in our next step. So what we want to do now is get rid of this composition. We actually want to put the elements of the LED here at the top of the PWM. So we'll go into the LED.h, we'll copy these LED members, and then we'll dump them into the top of our PWM class. Now notice that because these are in the same order, they look very much like an LED. And so because C will keep these objects of these members in the same order and they occupy the same number of bytes, when we pass a pointer to the PWM into the LED methods, the LED methods are none the wiser that they're getting a PWM because we have maintained the same size and order of all of these members. Likewise, we're adding the PWM values, our members down below. So we are essentially extending the LED class to include the number of milliseconds per cycle, the duty cycle, the time to delay on and the time to delay off, and the set duty cycle method. So let's take a look at how this looks differently in our implementation. So here's the new method. As before, if you pass in a null pointer to a PWM, it will allocate new space. And differently than before, we are not using a different pointer to manage this as if it was an LED. We simply cast the PWM as an LED pointer, and we pass it to LED new. And because we're passing in a pre-initialized value, it will now update the PWM with the initial values for an LED, and it will initialize the GPIO pin for us. As before, we override the blink method, but different than before, and I'll show you this. Different than before, we do not need to dereference the LED structure. We are going directly to the blink method. In other words, the PWM now owns this blink method, and we are overriding the blink method so that we can get our polymorphism. It looks like an LED, it smells like an LED, but it blinks like a PWM. And as before, we set the number of cycles, the number of milliseconds per cycle. We set the duty cycle, and then we call our set duty cycle method. And our set duty cycle method looks very much as it did before. One difference, and let's go ahead and take a look at that. One difference is that we are no longer having to dereference the LED because the PWM owns this delay member, right? Same thing with the state. We don't have to dereference the LED. It is part of the PWM to get the state. So let's see how that looks in PWM 2. So here we are. We set the delay on, we set the delay off, we set the duty cycle, and then we set the delay on the PWM. We don't have to dereference through the LED. If the state is on, we use the delay for the on side, and if it's off, we use the delay for the off side. Now let's compare and contrast our blink methods. So here's the blink method from before. Again, we had to dereference the LED structure and then check the last time, the state, and the delay, and then update the GPIO. If we look at the new method, not so much, right? We go directly to the last time, the state, and the delay. The PWM completely owns all of the members of this object. Now let's go to the main code and see how that looks. Down below, as before, we have the red LED. We don't have to cast this as an LED pointer. It recognizes that it's a PWM. Likewise, down here, we don't have to use a PWM pointer. It references it as a PWM. And we have our three blink methods. These two operate as before, as a little simple blinking LED. But here, when we call blink, it acts as a PWM. And the code is completely the same for all three LEDs. So let's go to the video and see how that looks. So as you can see, the yellow LED is blinking twice as fast as the green, and we are cycling through the duty cycles on the red LED. We get to 50%, and then we crank it down to 0 again. Success. So we have now completed the second part of our object-oriented programming in C environment. We have created a polymorphism. We can now treat our objects as if they were all the same, and yet they act differently based on the overrides that we've put in place. The next step is to create what's called inheritance. So that whole business of having to copy members around from one to the other is going to go away. And we're also going to abstract away certain elements. So we'll take the GPIO portion out of the LED and make it its own class, and then we'll inherit from that. And then the PWM class will inherit from LED. So we'll have 3 levels of inheritance. So tune in next time on part 3 of object-oriented programming with Dr. Frankentosh. As always, please don't subscribe to this channel. Don't like this video. Don't click up there or down there. Your time is precious. Please don't waste it. But thank you so much for spending part of it with me, and I'll see you next time on Dr. Frankentosh.